Chapter 2 has us delve into the basic atoms, molecules, and ions. I have broken this chapter up into two parts, so there will be two separate recordings. I have also uploaded two separate sets of PowerPoints because I just broke this chapter up. So in this chapter, we're going to be covering the atomic theory, the progressive structure of an atom, atomic numbers, mass numbers, isotopes, periodic table, naming ionic compounds, putting together ionic compounds, etc. So first we're going to start with the atomic. This is not a history class. I do not require you to know dates, but I will be giving you relative timelines of specific scientists we're going to talk about. It's not that I'm going to quiz you on it, but just to kind of have an idea of what was happening in different centuries in terms of science. The first thing I want to make very clear is that Dalton was back in the 1700s, late 1700s, late 18th century. And this was a time where being a scientist was not good. It was not, everything was very religiously based. And so they often didn't call themselves scientists. They were, a theorist, or sometimes royalty would look to them kind of like Nostradamus for understanding. They were often referred to as astronomers, studying the stars, when in real life, most of the scientists who discovered the majority of chemistry were actually physicists. There was no chemistry topic or label or definition back in the day. We're talking about with Dalton a time that there is no running water, there is no electricity, there is no indoor plumbing. We're ravaged with plagues and crusades and wars, just craziness going on in these times. Dalton was able to come in and by experimentation come up with the atomic theory. This is Dalton's atomic theory. You need to know this and understand it. It is based on a few laws that he came up with. One is the conservation of mass, meaning mass is neither created nor destroyed. Law of definite proportions and law of multiple proportions, which we'll talk about in more detail in just a minute. So first and foremost, the atomic theory consists of several things. First of all, an element is composed of tiny, indivisible, indestructible particles called atoms. All atoms of an element are identical and have the same properties, meaning every oxygen is exactly the same. Every carbon is exactly the same. Every nitrogen is exactly the same. Different atoms can come together to form compounds in small whole number ratios. There are no fractional parts because atoms are considered whole. So for example, H2O, water, CO2, carbon dioxide, small whole number ratios. Compounds contain atoms in small whole number ratios. We just talked about that. Atoms can combine in more than one ratio to form different compounds. So for example, hydrogen can bond with oxygen in water, H2O, in a 2-to-1 ratio. Hydrogen can also bond with chlorine atom in a 1-to-1 ratio of HCl. It doesn't mean the hydrogen changes. It just means it can do different things depending on what it's bonded with. The atomic theory was a huge, huge first step towards understanding everything around us. Now, you'll notice there are a few of these that are wrong. First and foremost, we know, if you've heard anything about quantum splitting, we know now, today, that elements are divisible. They can be destructed. So again, good first start, especially in the world of no running water, no vaccines, no medicine, no indoor plumbing, no electricity. He's figuring all this out. Based on the law of definite proportions, all this means is, depending on what I have, be it carbon dioxide, 123 grams of it, the mass of oxygen and the mass of carbon will change depending on how much I have, but the ratio always stays the same. Law of multiple proportions, same kind of concept here, where again, we have different stuff going on, but we maintain the same ratio. So Dalton had this fantastic understanding of the behavior of an atom. What would it do? How would it bond? What would the ratios be like? But he had no idea to explain what it looked like. So in comes a succession, and this is in order of first Thomson, second Rutherford, who studied with Chadwick, or Chadwick studied under him, and then Niels Bohr. So first we have Thomson. We're talking about 1820 to 1850s-ish. Thomson comes up with this plum pudding model of an atom. So basically what he said is, when he discovered that an atom has electrons, he discovered first that they are negatively charged. He discovered that an atom had protons, which were positively charged. And he surmised that they were just scattered amongst an atom in no particular order, no particular way. He used cathode rays and anode rays to really kind of figure out that one was positively charged, one was negatively charged, etc. And he was also able to calculate the mass of an electron and a proton. Thomson also had kind of an understudy, Millikan. And between the two of them, they were able to find this charge to mass ratio and the charge of an electron. And so the charge to mass meant what is the charge per mass of the element. I also just want to input a little bit of history here. Again, this isn't a history class, it's a chemistry class. The way colleges were designed and universities were designed between the 16 and late 1800s often meant you had one person that would study under another person. And once the understudy, if you will, got to a certain point or time of working with the authority figure, if you will, then that understudy kind of became the one in charge of research and doing all this kind of stuff. And then somebody else, another apprentice, if you will, would come in under that new doctor or scientist or PhD or whatever the category was. And in our world today, what that means is it would be like an undergraduate student doing research with a PhD professor. Okay, but there were no actual degrees like we call them today. There was no program requirements. There was no take these classes and get these credits. It was just, hey, let's go research this. So all of these scientists did everything 100% experimentally. We had this center where everything else around it was negatively charged, allowing the mass majority of the alpha particles, which are positively charged, to flow through by way of the negative electrons. So now they've shown, yes, we have negatively charged electrons that are circling the nucleus. Yes, we have positive protons that are in the nucleus. But then also we have these neutral neutrons that don't play a part in a charge, but do continue to add to the mass of an atom. By the way, that was late 1800s. Just to give you an idea of the size of a neutron compared to the size of the entire atom, here is this blown up, just to kind of give you an idea for ratio size. You do need to understand, you don't need to memorize these, but you do need to know how to use these masses and the effective charge, the mass charge, to be able to answer questions. After Chadwick had made his discovery about neutrons, we have Bohr that comes in, early to mid 20th century, so early to mid 1900s. He says, you know what, Thomson, you're on a roll. Rutherford and Chadwick, you almost had it. A for effort, but all of you are wrong. What he said was, yes, there is a nucleus where all the positively charged protons are located. And yes, there are electrons that orbit and surround the densely packed nucleus. However, these electrons aren't random. They are in fixed energy levels, fixed main energy levels. And within those fixed main energy levels, there are also sublevels, S, P, D, and F. S can hold 2 electrons, P can hold a total of 6 electrons, D can hold a total of 10 electrons, and F can hold a total of 14 electrons. I am going to upload a separate YouTube video to better explain this before we get into electron configuration. So keep an eye out for that in your folders. So now that we've talked about the progression of the model of an atom, now let's talk about how we use the periodic table to discuss and determine what we're going to do about the elements on the periodic table, how we're going to look at it, how are we going to read the periodic table. So first of all, I don't like how your book uses Z and A to describe the atomic number and the atomic mass. The atomic number in a neutral element, neutral is important. The atomic number in a neutral element is the number of protons in the nucleus of the element. It is also equal in a neutral compound, or I'm sorry, neutral element, to be equal to the number of electrons as well. The mass number is the total number of neutrons and protons present in the nucleus of an atom. So they use this A and Z generic notation. So where X is the elemental symbol, that's what we see right on the periodic table. For example, C for carbon, O for oxygen, N for nitrogen. That's the elemental symbol. And then we can say the mass number goes on top, atomic number goes on bottom. Mass number is the number of protons and neutrons. Atomic number is just the number of protons, and in a neutral element, also the number of electrons. So we can say hydrogen has a mass number of 1 and an atomic number of 1. Deuterium has a mass number of 2 and a atomic number of 1. This means, by deduction, deuterium has 1 proton, 1 neutron. Tritium has 2 neutrons and 1 proton. When you're finding how much of each thing is present, you can say, okay, this is protons plus neutrons, and this is just protons. So how do we figure out how many neutrons are present? Simple subtraction. That's how we solve for the neutrons. I want you to go through these sample problems. They are in the PowerPoints. The setup and the solutions are present. I am not going to go through them with you. They're very straightforward. It's just practicing figuring out how many neutrons are present and isotopes. So for example, here you see that these are both chlorine atoms, elements. You're going to find I intermix atoms, elements, molecules, etc. I really do mean the same thing. I'm just trying to be consistent. So this is a chlorine atom. This first one here is a chlorine atom that if I just do simple subtraction, let's see really quickly, 35 minus 17 has 18 neutrons. And the second one here is just 37 minus 17 has 20 neutrons. That means these two chloride atoms are isotopes. They have the same number of protons, different number of neutrons. I also want to mention that all of these, I didn't mean to do hydrogen. All of these are metals. Then you have your metalloids or semimetals right here. These either behave as a metal or a non-metal depending on their environment and what they are being reacted with in the conditions. And then we have non-metals. Okay? Now, most of the metals, let me rephrase, all but one of the metals occur naturally in nature as a solid, except for mercury. This one occurs naturally in nature as a liquid. All of the metalloids or the semimetals are as solid naturally in nature. The non-metals, except for one, will occur naturally in nature as a gas, except for bromine. Those are the two liquids on the periodic table. I also want to mention to you about the 7 diatoms. They take the shape of a 7 on the periodic table. Oh, and don't forget hydrogen. What this means is naturally in nature in their gaseous form, they take a chemical formula of N2, O2, F2, Cl2, etc., which just means 2 of them are bonded together naturally in nature. Okay, those are your diatomics. You need to memorize those. The last thing I want to mention to you is that I want to remind you that even though naturally occurring in their normal state is solid, liquid, and gas, that doesn't mean they cannot go on and with heat and cold be transformed into other states of matter. Okay, so this ends chapter 2, part 1. You should find another video of chapter 2, part 2. For that one, I highly, highly, highly recommend printing out those PowerPoints because it's a lot of information to cover, a lot of math heavy stuff, and not math heavy, naming heavy. And also I have uploaded a bunch of helpful or useful information, kind of practice worksheets for you with fully written out keys, and also kind of cheat sheets for things like naming and that kind of stuff. If you have any questions, please feel free to email me, and I'll see you next time. Talk to you soon. Have a good week.